Alright, okay. Feedback on the KA8, the amines KA that you've done recently. Alright, so multiple choice questions first. First one, you needed to be able to recognise that if you've got a primary haloalkane, which you have there, you're going to get a primary amine. So that's why the answer is A. This one wasn't done, a lot of people didn't get this right, so you need to have some kind of strategy for when you're looking for chiral centres. I've tried to sort of give you a kind of procedure. Look for single hydrogens. So I've put all the hydrogens in because that helped me look for them. Then look for the single ones because there will be probably a chiral centre where there is a single one. Don't bother with anything with a double bond or two hydrogens attached, and then have a look at any other carbons, okay? And then you'll find that there are actually 6 chiral centres on that molecule. Question 3, this is phenol reacting, so it reacts more easily than benzene, so we don't need the concentrated acid that we require when we're reacting benzene. But we do need the HCl and tin, so that's it. Basically, you need to learn those conditions for different reactions. Given a skeletal formula, and then you're asked which statements are or is correct. So you should recognise really straight away that there is definitely an amine group there, so you know number 1 applies. There is no carboxylic acid because that C double bond is not here, which is where it would be if it was on the end of the molecule, if it was an acid. And the amide, the C double bond O, has to be next to the nitrogen, so the nitrogen would have to be here next to the C double bond O. So D, only 1, okay. Right, okay, so now we're sort of getting into some of the more meaty questions. You're given a formula, structural formula there, or skeletal formula rather, for salicylic acid. You're asked to define condensation polymer, and a lot of you didn't mention that it is a monomers, you know, many monomers joining together. And in terms of condensation polymers, you lose a small molecule, maybe water, maybe HCl. And it would be the same if you were being asked about addition polymers. You always have to start by saying that it's a number of monomers joined together. Okay, learn those definitions. I can't stress it enough, really. Okay, you're given a repeat unit of a condensation polymer that has got an ester link here, yeah. So you're asked to draw the skeletal formula of 2 monomers that can be used. So you need to break this up into the 2 monomers that actually gave you that repeating the unit. And you're asked for the skeletal formula. Now, I don't know about you, but I'm not very good at visualizing stuff, skeletal formulas. So we know that an ester link has got to be a carboxylic acid and an alcohol. So basically I've just split this into the alcohol and the carboxylic acid, but I haven't drawn it or a skeletal formula. Well, this one is almost skeletal, but it's not quite. So just to identify to the examiner that I'm not asking them to mark those 2 formulas, I've just crossed through them and then I've put my skeletal formula underneath. And that's perfectly acceptable to do that. Make it absolutely clear what you want marked. And you don't have to scribble it all out, just put a line through it to make it clear you don't want it marked. Okay, so this question, we know the formula of salicylic acid, we've been given it at the beginning. We're told it reacts with 3-hydroxypropanoic to form a mixture of condensation polymers. Okay, and it says that they react in equal quantities, obviously. They're asking for the repeat unit of this polymer. Yeah, so it's important that you just show the repeat unit. But first of all, I mean, these condensation polymers, you know, can be complex. So I would always, to make it clear in my own head, draw out my 2 monomers to show myself Right, where is it actually joining together? We know we're going to lose water, so we've got this here and we've got this here. This is our ester link, C double bond O O. Yeah. But because you're being asked for a repeat unit, it's very important that you don't put that those last hydrogens here. Yeah. Okay. That are actually in the formula, because you're showing a repeat unit which is not the complete molecule, so you need the trailing bonds at the end. So obviously there are two possibilities here, depending on how you joined your two monomers. So you can do them in this direction, or you could do this acid group here could join to this alcohol here, and either of them are correct. Okay. And again, I've just drawn them out and shown you exactly where we lose the water from to make it clear where the join is. Yeah, and do that in the exam if that's what you need to do, but you do need to get, you know, quite fast at drawing them and confident at drawing out the structures. Okay, so we're given some amino acids here, 3 amino acids. Dipeptide, yeah, is basically 2 amino acids joining together. Yeah, if it was a polypeptide, it would be a polymer and you'd have your trailing bonds, but you don't here. Yeah, because this is, this is in your textbook, so please make sure that you are up to speed on the you know, these kind of, when they use this kind of terminology. Okay, so again, you're just taking these two structures here, recognizing where you're losing the water, and then joining them together, and then swapping them round and getting the same condensation polymer. Okay, so yeah, I've just kind of listed here the approach you should take. Draw out your monomers. If you're not sure, take off the water or the HCl, depending on what it is, and then join the two molecules together. Depending on what you've been asked for, you either show trailing bonds or you don't. In this case, you don't. Isoelectric points, basically you need to learn, you know, how the amino acids behave, what they form at their isoelectric point, and then how they behave if they're in an acid or an alkaline solution, which is what you're given here. So you're told the isoelectric points of these two amino acids. You're asked to draw the structure of alanine at pH 6, which is its isoelectric point, which means it's forming the zwitterion. Yeah, so you've got the positive, the hydrogen from the oxygen has protonated the nitrogen, so you've got your positive charge there, your negative, that's your zwitterion. But for the serine, they've said at pH 10, obviously that's an alkaline, it's behaving, it's going to behave as an acid in an alkaline solution. So this is what your zwitterion would look like for serine, behaved as an acid, so your NH3 plus, which you would normally have here in the zwitterion, has lost a hydrogen, i.e. it's donating a proton. Yeah, but the negative charge stays on the oxygen, but nothing's happened to that. Okay, again, you look in your textbook, you know, you kind of just have to learn how they behave in those different environments. And then you're given the structure of proline, and then it says that they can form a polymer, and to draw the structure of the repeat unit, only one repeat unit. Okay, again, I can't do this myself without drawing them out. I can then see what I've got. So I've drawn two proline molecules, and because you're only asked for one repeat unit, you need to make clear what you actually want marked here. So I've drawn them out together, taking it from here. I've put this bracket round to indicate that that is my repeat unit. Notice trailing bonds here, so there's nothing here and there's nothing here. Or you could cross that out and then draw a repeat unit and actually draw attention to the fact that that is one repeat unit. Okay. Question 7, you're given the structure of tartaric acid. You're asked for the empirical formula of it. Now, obviously, you need to know the definition of empirical formula, which goes back to September 2 years ago, I think. Yeah, 2016. Yeah, and you should know this from definitely from your AS year. So, molecular formula is C4O6H6. The empirical formula is the lowest whole number ratio, so you just divide it by 2. Systematic name for this is, you can see it's a diol and it's a diacid. Yeah? So our alcohol groups are on carbons 2 and 3. So basically 2,3 dihydroxy. We have to use the prefix here because the suffix is taken by the acid suffix. And the mark scheme did allow you to say butane 1,4-dioic acid, but you have to remember the dioic bit. Okay, so yeah, if there's 2 alcohols or 2 acids or whatever, it's either di, tri, tetra. You have to include that in the name. Okay, so you're told that this tartaric acid up here reacts with 1,6-diaminohexane, and you're given the structural formula. 1 repeat unit again, make sure that you only draw 1. Yeah, so I've done my monomers again to show myself where I've lost my water and I've just joined them together, but you've got the trailing bonds. So the polymerization, you're told here, takes place in 2 steps. At first, tartaric acid and the diaminohexane react to form a salt. Now, if it's a salt, you must have a positive and a negative ion. Yeah, so you just got to ask yourself how you can form a positive and negative ion from these 2 monomers. Yeah, and I don't know, the obvious way to me, maybe not so obvious to you, is to protonate your nitrogen from the acid group. Take the hydrogen off there, protonate it, and you've got a positive ion and negative ion. Okay. So you kind of have to you've got to apply some chemistry knowledge here. Okay, amino acids again. You're given the formula for serine. You are asked for a definition of an optical isomer. Now, a lot of you did not. You said mirror images, yeah, and you talked about chiral carbons, but what you didn't say was non-superimposable. You must say that they are non-superimposable mirror images of each other. They are also called enantiomers, but that, they needed that. You needed to have those words in the definition. Please learn your definitions. You're asked then to draw the 2 optical isomers of serine. So please watch the Boomer Chemistry video if you can't remember how to do this. He makes it very clear. I've written instructions here. You draw the 2 bonds in the plane of the paper first. Going on what? This one. These are obviously identical. This one and this one are going away from each other in opposite directions. Then draw the wedges in, going away from you, coming towards you, and then put in the groups. The important thing is that the groups have to be on the same bond. So on your wedge coming forward, I've got COOH, and on this one I have to also have COOH. And if you look at this, you can see that if this was a mirror, this is a mirror of this. This is in the same place, and this is in the same place. So you have to use your common sense here as well. Think about what something looks like in a mirror. And the other thing that he did say on the Boomer video is if you extend this and extend this, that they would cross. They would not run in parallel. Yeah? So bear that in mind as well, please. Otherwise, that's 3 easy marks to draw an optical isomer like that. Okay. So you're told that serine can react with another acid, another amino acid, to form 3 different organic products. So you're given the molecular formula and then you're asked to draw them. Now here again, I've drawn out my 2 monomers to see what's going on. So I've got an amide link here, C double bond O and nitrogen. Yeah. Then all I've done is swap my monomers round. So I've got now this end reacting with this end. Yeah, so that's 2 of the isomers. done it exactly the same way. And then the third one, obviously, you need to recognise that there is actually an alcohol group here, yeah, on this one. So that alcohol group can react with the carboxylic acid group of the other one to form an ester, yeah. And there's your three products, basically. Yeah, yeah. Okay, your organic products. Okay. Right, question 9. I was a little bit surprised that I don't think anybody managed to calculate what 90% would be, a 90% yield from this information you're given, 8.10 grams of pure aspirin. So basically this 8.10 grams, 0.10, is 90% yield, isn't it? Because you're preparing that much, so you need to know how much to get a 90% yield that produces 8.10 grams of aspirin. And tells you in your answer you have to include the mass of hydroxybenzoic acid needed and the purification steps from the hot reaction mixture. Now we have just done this when we're making the benzoic acid, so you should have been familiar with these purification steps and been able to give it a good go to actually put the steps in. A couple of you did, but not many of you. So this is a lesson for you. You must take note of the practical work that we're doing, the equipment that we're using, the process we're going through, why we're doing it. If you've got this asterisk up here, this star, they want an extended answer that shows, you know, some coherence. Okay. All right, so I've worked out how many moles of acid we require. 0.05 moles, 45 moles, yeah. But this is only 90% of our yield. It's a 1-to-1 ratio, 2-hydroxybenzoic to aspirin, yeah. So we're going to need like another 10% worth of the 2-hydroxybenzoic acid. So we need to multiply that up effectively. So if you put 100 over 90, because we actually want 100%, we recognise that we need 0.05 moles of the 2-hydroxybenzoic. Convert that to grams by multiplying by the molar mass, and that's 6.9 grams. So we know how much hydroxybenzoic acid we need to start with. And then you're asked for the steps for purifying. Basically, if you think about what you did, the mixture cooled down and crystallized, and then you filtered it under reduced pressure using a Buchner flask and funnel. Yeah. Don't forget to say under reduced pressure, because that's basically saying that you used a vacuum pump of some sort to reduce the pressure. Then, once you'd got your impure substance, you dissolved it in the minimum amount of hot water. I mean, depending on what it is you're making, it may be water, it may not be, but in this particular case it's exactly the same as the benzoic acid. So you had hot water in the minimum amount of hot water, okay, and then you allowed it to cool and the crystals form. They're your pure crystals, and then you filtered them again under reduced pressure and washed them with ice cold water and allowed them to dry. And they are exactly the same steps that we used for the benzoic acid, okay. So do take note of the practical work as we do it and why we're doing it. This question was not answered well at all, and I think it's because the molecule just looks horrible. And I did say this to you in class, that they will give you horrible looking molecules, but you have to be able to recognize functional group, the bit that's actually important. Okay, so this is about acid hydrolysis, yeah. So acid hydrolysis in relation to amides and esters, yeah. And an acid hydrolysis is you're basically putting back water where it was lost. So when this ester link was formed, you know, we lost water, so we're going to put the water back. That's all you're doing, yeah. And the same for your amide. When you form your amide, you lose water, so we've just got to stick it back in. So you're looking for those groups. First of all, identify them. So where would it break? So I've put this line here just to show you where the bonds would break. And if we hydrolyze a polyester, then we end up with an alcohol and an acid, yeah, in ester hydrolysis and amide hydrolysis, we end up with an acid and an ammonium ion. So here's our alcohol. We add an H on there, and then we're going to add OH on here, effectively, yeah, to get the acid bit. So here we are. That's the alcohol. Here we've got our carboxylic acid. The mark scheme allowed, if you didn't remember, that your nitrogen would also be protonated, but the mark scheme allowed you not to include that. But you still got the mark if you didn't include it here. Okay, so NH3 plus, and then obviously the amide bond breaking here, and then what are we forming? We're forming an acid. Yeah. So here, this is basically it. And again, they allowed you, if you didn't protonate this nitrogen here, you still got the mark. Okay, so here I've added the hydrogens in. But that's, so they are the three products that you would get from hydrolysis of this. And the key to this was recognizing there was an amide group here and an ester group here. And obviously then we're going to end up with this alcohol broken off. And you're adding the water back to those two. So it's recognizing the functional groups and using your knowledge of acid hydrolysis, of course, or base hydrolysis. You know, you've got to know that, otherwise you couldn't answer those questions. Okay, question 11. Right, you're asked to name that. It's a primary amine, so it's dimethylamine. Some of you put NN, I think, or N dimethyl, NN, I can't remember how you, and I think some of you I did actually give the mark, but I'm not sure that you would get a mark for that, because for a primary amine you don't really need to use the N notation. Okay, so again we're given this is a secondary amine, saying that this can be formed by reacting this primary amine with this haloalkane. Yeah, name and outline the mechanism. So this is substitution. You know, a number of you put addition, I think. We're substituting our bromine for this amine. Yeah. So there must be some attraction for this lone pair, and obviously it's this slightly positively charged carbon here, and then the carbon's not going to make 5 bonds, so the bond will break for the bromine. And a lot of you actually got this part of the mechanism, so that's good. You managed to pick up 2 marks there, and some of you did get the name. So then we are left with, because our nitrogen now is making 4 bonds, got a positive charge on it, so you'd have your amine would come in and take the hydrogen, and this bond will break and go. So your curly arrow must go to the positive charge. Yeah, and that gives us the product that we're looking for. Yeah, our secondary amine that we were asked for up here. Okay. And then the next part of the question is kind of a little bit of an extension. Name the type of compound produced if a large excess of the haloalkane was in with the mixture. Yeah, and this would actually form this quaternary ammonium salt. So it would basically keep substituting. The amine would keep substituting whichever amine it is you're using until there are no more substitutions to make. And in this case, ours was methylamine. Yeah, so we end up with 4 CH3s on here and positive charge on the nitrogen, and the bromide ion is the other bit, the negative charge. Now it's best to just bear in mind this is exactly the same as free radical substitution when we looked at alkanes all those months ago. It keeps substituting unless they change the conditions in the reaction mixture. It will keep substituting. Okay, and then the last question was about the reaction of an acid anhydride with an amine. Okay, we've got the same amine, obviously, our ethanoic anhydride here. So I've just drawn that out and shown you where the bonds would break. And the what you would form here is your secondary amine and your acid. Okay, And this is the same reaction effectively that you get with an acyl chloride. And yeah, same reaction with an acyl chloride. Okay. Right, so that's the end of the paper. Obviously you need to go through everything that you've done here really carefully. Not many of you got a mark that you're probably happy with. Okay, see you later. Bye.